up. Okay, everyone, welcome. So Nitesh is asking some questions that we can address and then start our class today. So one question he has is why we are doing the simulations and what is the basically, from what I understand from his question, he wants to ask what is the meaning of these simulations in the real world, where does it apply and all. If I'm correct, Nitesh, do type yes if I am getting the question correct. Okay. Uh, so why we do these simulations? Firstly, uh, all the things that we see uh, in the practical world, these can't be predicted, right? So there, in terms of suppose slope stability, or in terms of strength of a material, in terms of how a fluid flows from one place to another, in terms of how we design any equipment, suppose our shovels or dumpers, how much load they can take, how long they can run, what will be the what will be their outputs and inputs in sense of how much efficiently they will be able to work and so on. So there are so many variables and there are so many things in the real world that we generally can't predict by just giving certain equations. Okay, this is the practical problem. Like suppose I want to calculate what how what I want to find out how much diesel fuel will be required for 1 month of my dump truck movement, suppose. So there are so many variables are there, right? There can be certain equations that are already existing. For example, there are empirical relations that are directly relating the fuel consumption with what is the speed of that dump truck, right? What is the distance the dump truck takes, or how much load it has. There can be equations that are defining that. But there can be other factors as well, right? Like what is the aerodynamics of that dumper, how much wind resistance it is facing, what is the friction between the tire and the haul road, and so on. There can be so many factors that are there. So simulation, what it helps is basically in many of these situations, it basically helps us to understand how things will behave in a practical world without actually seeing those things in reality. So suppose we want to see suppose we want to see a ventilation model in an underground mine. So we can design a mine based on our what kind of distribution coal is, or what kind of distribution our mineral is, and we defined uh, all these galleries and all these cross cuts and everything. We defined all the design is prepared. But how do we know that at a place where I will be working at last, will some air or will proper ventilation be reaching? So if I want to do an experiment on that, either I have to make a very small scale model, right? A physical model. So that also is done. That is called physical simulations. So simulation basically in that sense that we want to basically recreate in some way or the other what actually the situation will be. So physical model recreation is very nice sort of experiments where we do it on a small scale in laboratories. So we may make models of that and see if I use certain amount of pressure, if I use certain amount of ventilation stoppings, certain amount of resistance is put in between, and so on. So how much air is reaching, how much oxygen is reaching, will it be sufficient for workers to work, is the ventilation proper, and so on. And if not, if physically sometimes most of the times it's not possible to do it in physical models, we go for numerical models. So numerical simulations are there. So numerical simulations, basically what we could have done in physically, we actually simulate in computers. So the whole purpose is basically to find out or replicate a real world situation in some form or the other in form of either physical ways or computational ways. And that's why numerical simulation basically gives us an idea what will happen. I'm sorry for taking it so long. Nitesh, did that answer your question, what you wanted to understand in this? Nitesh?
Hello.
Hello? Nitesh? Yeah.
Sir, numerical simulation and numerical modeling, are they same or different?
So numerical modeling and numerical simulation are similar. Basically, these are two parts of the same thing. Numerical modeling, we make models based on what kind of equations or what kind of things that define that numerical model, basically. So suppose in case of dump slope stability, our numerical models will be based on the strength equations or the elastic equations of that material, right? So numerical modeling will be a constituent term, including defining of geometry, defining of the boundary conditions, defining of the what kind of equations are defining that activity. Suppose in ventilation, there will be these equations that define the flow of fluid, right? So all these, including the geometry, defining the geometry of that problem, defining the equations that define those situations, and some what are the restrictions that or the boundary conditions we call. So all this, including, is called modeling, and the actual work, the whole part of it, in a combined way, it can be said as numerical simulation, like right from the modeling to basically processing that data to interpreting that data and finding visual aids to understand that data. All this included in numerical simulation. Okay. Did that answer your question, Nitesh?
Okay, sir. Thank you, sir.
So those were the questions. Anything else?
No, sir. No, sir.
Okay. Okay. So, students, do feel free. Nitesh tried to ask some questions that is so good to hear. Do feel free to ask anything because these topics need to be understood thoroughly. Why we are doing it? What's the whole purpose of this computer application in mining subject? Is it any use or not at all? Like you should be uh, we should be knowing why we are doing these things. It's like not just to score marks, right? So these are useful skills we are developing, why we are doing all these, why we are learning this subject, where it will be useful. Will I be actually using it in field or just I'm doing it here? So many things are done actually just to understand also. The theory part is also important. But also why we are doing and learning each subject, we also need to understand that. Why we are doing all these exercises of understanding how a probability analysis work or so on. So all these skills or all these understandings will be useful when we go ahead and do our actual analysis, like for example in slope stability or in maybe in numerical modeling of ventilation or a pit design. So do keep your mind open. Do ask questions. Always keep on asking questions. Why we are doing it? Why this is there? Why this kind of model we took? Why this value we took? Do keep on asking that, and the answers that come out of that, those will actually be helpful for us. Okay. On that note, let's continue for today's class. Uh, Yesterday, we basically stopped in between our exercise. What we were doing was uh, trying to find out how we make the probability analysis work, right? PDF generation and all. So we yesterday we reached at a point where we generated some random numerals that we saw were done in Monte Carlo simulation in probabilistic analysis, right? And we also saw how a curve fitting works. So in MATLAB, so we saw various ways in which a curve fitting can be done. We also saw what is the criteria of judging whether a curve is properly fit or not, based on r square and adjusted r square values, the goodness of fit that we were seeing, right? We'll also see that a little bit more today. Why we are doing this? The purpose was to basically see whether we can actually do the probabilistic part that we learned, um, based on our uh, limited functionality that we have in terms of softwares, right? So that's what we were doing. So that also helps us in understanding what these PDFs and all these means, probability distribution functions, how they actually interact with each other and so on. So what we'll be trying to do is today we'll be generating PDFs. Yesterday we generated for one variable, right? Cohesion. We found out what were the equation of that in terms of Gaussian fitting, normal distribution fitting, right? And we also found out uh, what were the coefficients of that equation, so that we can actually we actually got a PDF like for probability distribution function for that cohesion. So today what we'll be doing is we'll be trying to see how these other functions can be plotted, right? We'll be also plotting for cohesion, sorry, for friction and unit weight. And then what we'll be doing is we'll try to find these resisting forces and the other driving forces that was there when we were talking about factor of safety calculation, right? So if you remember, in the probabilistic analysis, one part was where we actually did the calculation based on these probability distribution functions, but uh, uh, just by using the factor of safety formula. So on the basis of that, we actually plotted these driving forces and resisting forces together, and we found what is the overlapping part, and that was actually giving us the probability of failure, right? So we'll try to do that. Let's see how much it can be done. I've also not done that in MATLAB. Actually, I did it in last long time back uh, in uh, in other software. So let's see if that can be done today. We'll be doing that, finding out the probability of failure, and if possible, we'll do the factor of safety calculation on that. And if time permits, we'll also start the finite element method. So limit equilibrium method we have already seen. We have also seen the empirical method, or the deterministic method, where we actually found out the factor of safety by manual calculations, right? And then now we move ahead, we move on to a new method called the finite element method. What it is, how is it different from limit equilibrium method, what it entails, how is it done, where is it applicable, and so many things. Those all we will be covering from uh, starting from the finite element. Okay, so this is important type of method, very important in very type of simulations, and relatively has higher accuracy and uh, more versatile kind of method. So we'll be discussing that. Okay, so let's move ahead from yesterday's work. Yesterday we yeah yesterday what we did was, so we found out this uh, random number generation function we found those, and on the basis of that we actually uh, found 100 values that were randomly generated but were distributed in a normal distribution fashion. So normal distribution fashion is, now we are well aware of how it looks like. We found out how it behaves in terms of frequency. We converted the frequency into probability, and we actually did a MATLAB exercise where we found out what will be the defining equation. Why we found out what will be the defining equation? We actually wanted a single PDF that we will be using for further calculations. Now, go a little bit further, and let's do this exercise for other variables as well. So I have some things already done so that we can be quick in this. Uh, we have some values of C, some values of I, and some values of unit weight. Let's use those. And on the basis of that, we can actually do the whole exercise. So, yeah. I'm just copying the data. So I have these values that are randomly generated for C, phi, and unit weight. How is unit weight in negative? Okay, that's my mistake. So I have to basically make D. Okay, and apply here also the same thing. Right. And here it is A. So copying and pasting, there will be some issues. So you have to take care of that. Okay. Let's do one thing. Let's rather than it keep on changing, what I can do is make them constant. So let me make 100 total 100 variables, right? It is starting from 3, it can end at 102, so total 100 variables are there. And in place of it randomly changing, I will paste as values so that it remains constant. Okay. So what basically I have done till now is found like yesterday we generated 100 random variables. Similarly, we have generated 100 random variables for C with a mean of 40 and a standard deviation of 1.5. So it's varying with like 5 points in this side and 5 points on that side. So maybe 35 to 45. Okay, that is C. Phi also we have done similarly. It is varying with a standard deviation of 3 and similarly unit weight. So unit weight is deviating with a standard deviation of 2. So that's just to make some random variables. So now what we have to do is we will to quickly find out what is the maximum and minimum values. So we know maximum and minimum values for all these. It is basically from 35 to 45. So let's put 35 to 45 values. All right. And for the, this is for C. Let's name it as C bin. Let's name the other as phi bin and unit weight win or the UW win. Correct. So unit weight varies from 32 to 38. So I think I'm doing it right. Yeah. Let me have a check again because variations are same, I suppose. Okay, the good way to do it if we are not sure what is the variation, I am also taking it as random variables uh, somewhere generated. So what I can do is max and min function, right? I can find out the maximum values and minimum values. Oops. Right. क्या हो रहा है भाई? अच्छा, okay, sorry. So we have maximum and minimum values 35 to 42. So our distribution is correct. We can do that for C and phi also. So it is varying from 26 to 41. So let's distribute in uh, 25 and 42. Let's do that. So 20, let's do from 24 to 42. How many will be there? 24, 26, 28, and so on. 9, okay. And what is for unit weight? It's from 18 to 28. Let's vary it till 17 or 18 to 29, probably. Simple. So basically we are making bins on which ranges can be distributed, right? Uh, so that will be easier. Okay, this is done. Now very simply we do the histogram analysis, and let's not make the histogram this time. Let's just find the values. Okay, so first one is with these many ranges. Oh, okay, my mistake. First one will be this, and bin range is, and we need an output range. So output range will be here, and we don't need any other one. We just click OK, and it's done here, right? Similarly, we do for others. Let's do it quickly so that we move on. Mm, This is for G, so this, and these are from fire bin, and this one is the output, correct? And the last one, this is I, and this is also I. Bin values given and given output range. That's it. So we got the distribution. So let's import these now in MATLAB. We have to save this and keep this a little bit. Okay, where is MATLAB? Yeah. So MATLAB, what we'll do is we can directly import, like yesterday we saw how we can directly import it. So we will directly import today, and we'll open this. It will open. Okay. So anyone has heard about Murphy's law? किसी को पता है Murphy's law क्या होता है? Murphy's law says that everything that can go wrong will go wrong. So This used to work pretty well. Okay, now it is done. So not everything goes wrong. That's okay. Anyways, so where is the import part? Okay, so let's import this. Uh, correct. So we have on sheet 3, no, sheet 2. Sheet 2, we have our today's data. So today's data, let's change the names for the CX, CY, and so on. So we can we have to first change the column vector and then change here. So this will be CX values, right? CX val. This will be CY val. These will be phi x val. These will be phi y val. Oh. And these will be UW, unit weight, X values, and let's name this UW, Y values. Okay, now start importing. Just select and import. Simple enough. So it will, as soon as it imports, it will confirm. This one is imported 11 by 1. So we are hoping that Y value also will be 11 by 1. That's true. Again, we import for phi X values 11 by 1. Oh, 10 by 1 this time. Y values also, and Z. Oh, sorry. Unit weight. So unit weight we took, and Y values all done. We basically go to see which all are there. What happened here? We did something wrong, I think. Hold on. So all are column vectors. So yeah. We have C values. CX values we can see by double clicking all these values. We can actually see the vectors here. Phi X values. Now what is happening is this is a different format or same format? 10 to 1 double. So same format, that's okay. Why it's taking a different form? Strange. Anyways, yeah. So all values we have, X, Y values of C, phi, and unit weight. What we will do now is we'll first change the Y values to probability functions. Now, why we are doing this? Yesterday, I am not sure I made the I explained it, but here, if you see, every Y value is basically distributed into as a total number of frequencies or total number of values that we generated, right? So if we are generating equal values, then it doesn't make any difference because uh, we are basically distributing it in a normal distribution for all. But what is happening is on the X side, you are seeing each and every one has different X values. So basically, X for cohesion is varying from 35 to 45, while for phi it is some different value, and unit weight it has some different value. So what happens is when we do a probability distribution work, we actually want to basically normalize the data so that it can be compared with each other. How we do that? Basically, we do it on the y-axis. So on the y-axis, it can be on the same line. So let's do that. Let's change the y values to suit our probability distribution function. So what we have to do is we have to divide it by n into w. That is number of values. So total number of values for all mostly are sorry for total number of values for all of these are 100 because that's what we chose, right? We generated 100 random values and the difference between each of these ranges. So now you see the cohesion range and the unit weight range is already 1. So it's not an issue. But here what we have done is we have taken a 2 difference in phi. So that we have to factor. So what the cy values will be basically dividing uh, C, let's name it as cy probability distribution values, PD values. Okay, cy PD values equals to, we can bring that cy or val here directly, divided by 100. So 100, why we are doing? Number of values is 100 and 100 into 1 basically means 100. So 1 is the difference in each of these x values in ranges. So that works for us. So the new CYPD val variable is made. Okay. So similarly we do for others. In phi PD val, phi y PD vals, let's keep the convention same. Is will be equals to, we bring the phi y vals and divide it by 200. Why? Because 100 is the numbers and 2 is the difference between each of the x values of this. So that changes, correct? And similarly for unit weight y vals, y PD vals, so that will be unit weight y val. I have named it wrong. Okay, anyways, by 100, because this time also 100 variables and one difference. So that's it. We have our two variables. Now we go for the curve fitting part and quickly find out the best fit in terms of Gaussian fitting. So yesterday we saw how this curve fitting was working, how this curve fitting app works for us. Let me reduce some tension on my computer because so many applications are open. Probably that's why it's slow. Hold on. Okay. Anyways, so let's make the first fit as CFit, and X data is CX, and the Y data is CYPD because that's what we are plotting. And as soon as it does, it tries to basically fit whatever first it has. So polynomial it has, so it tries to fit polynomial. But what we want to fit is a Gaussian distribution because we are aware that it's some sort of a normal distribution function. So that will give us a better fit. So now we are seeing the goodness of it. So now if, as I was discussing yesterday, based on what kind of values we are getting for R square, adjusted R square, RMSE and SSE values, we can this all values basically gives an idea of what is the goodness of fit or the what is the type of fitting that we are getting. Goodness of fit basically means indicates how well our equation represents our data. So this equation with these variables is almost 98% certain that it can predict any data that falls with respect to our data distribution. Okay, so that's good enough for us for our exercise. We for many other prediction exercises, like we may have to make some toolboxes which can actually predict weather and all. So based on what kind of application it is there, these kind of regression or curve fitting always takes place. And in those cases also, we may have to rely on a certain R square value. So sometimes even a R square value of 70 plus is considered quite representative. But sometimes, like in our case, it's not at all close. So based on what kind of data we have, what kind of threshold we have set, that all defines uh, what is the acceptable R square value for good fit. Okay. And yesterday I was also talking about adjusted R square. So adjusted R square basically tells us the R square based on the number of coefficients that are there. So if yesterday, like we were discussing, if I add more coefficients, so like we have uh, uh, two Gaussians fitting in this. So you can see how another Gaussian might have fitted somewhere here, and a Gaussian might have fitted somewhere here. So combining these two, they have tried to fit our data. But what happens is the adjusted R square has not much effect as compared to before. Uh, so so that ways actually it is giving a better fit. So that ways we can actually judge adjusted R square. But right now let's keep it at 1. Let's take these equations, these coefficients for our C, and copy those in our Excel file so that we can use them to further work on our equations. So these are the values for C. Uh, we need just these three because, as I was telling, the confidence intervals basically gives us 95% confidence between these two values. So these are statistical requirements. If we go into deeper into statistics, we might want to understand. So anyone who is interested, they can, but we won't be covering it here. So another fit, the next fit we will be doing for phi values, so phi and phi x and phi y PD, and we also got a single Gaussian distribution with 96% accuracy this time. Again, 95 plus or 90 plus we are accepting right now. So it's quite good for us. We'll take that. Let's copy these values of AB, A1, B1, and C1 and paste these below for phi. And similarly, we do for the unit weight. Oh, sorry. X values on the X side and Y values on the Y side. Right. This data is also very roughly distributed well. But anyways, we are getting R 90%, not that good. X is normalized by the mean of 23.5 and standard deviation 23.6. That's okay. So let's take these values, try to find out what we are getting, and paste it here. So what these values basically represent is, as we saw in the Gaussian fitting, we already had this equation. So this equation is actually same equation of the normal distribution. If you remember normal distribution, it was something around 1 per 2 pi sd e to the power minus x bar over sd. So similar to that, it has basically replaced 1 per 2 by sd in by a1, x minus x bar. So mean will be b1 and c1 will be some demonstration of a standard deviation or close to that. So that ways it has basically converted into equations and tried to find out what is the best coefficient. Let's extract these values of a1, b1, c1 quickly. and use those, and I will show you how these can be actually used uh, to define equations in MATLAB. That is a very useful thing to do in MATLAB, defining equations, and on basis of those equations, basically we can uh, find out or plot various variables, various equations directly. And for these probability distribution equations, plotting these is as important as calculating. So we'll be doing that. Just let me extract the values of A1, B1, and C1 for C, phi, and unit weight. So let me remove those. Again, distribute these as and convert it into columns based on the spaces, and copy these values here. Remove this and last again for unit weight. Perfect. So we have three coefficients for the defining equation of PDF, the probability distribution function that defines cohesion, friction, and unit weight for this set of problem. So how what to do next now? What we'll be doing is let's now move on to script. We are basically now trying to first plot these values and try to make an equation out of that, so that we can actually work by adding these equations and finding out the uh, factor of safety, and before that the forces. So let's start with a new script, and just in order to see what's going on, इसको save कर लेते हैं. Let's save this. We first, what we'll do is, let's define these A1, B1, and C1 first. So uh, how we do it, at CA1 for cohesion equals to maybe let me copy paste this, that will be easier, right? And hold on, C CB1 is can be this, and C1. Okay. So he what we are doing, we are right now defining these coefficients in this script, our MATLAB function. Okay. And based on that, we'll be making our separate equations. Just in a few moments, you will understand why I am doing this. Uh, Let me just put these three, and so this is CA1, this is phi. Okay. Okay, and this is U, unit weight, right? So CAP, and let also change the values. Quickly. Um, this, right? And for the last one, Right. So now once we have defined this, let's first save this because we have to do some other work in this. Sorry. Okay. Let's save this as something. Probability analysis try, right? Probability analysis. Prob and now. Okay. Prob and A1. Let's save it here. Uh, Now, an important thing that we were just leading all this to here is how we basically define an equation in this. So, if we want to suppose make a certain equation like y equals to mx plus c, right? So y equals to mx plus c, basically, if I type this here, all the values of here, all the values will be taken as constant. So for MATLAB, y is also a constant, or sorry, a variable. M is also a variable, x is also a variable, and c is also a variable. So if it basically won't be able to plot in terms of y versus x that we want to do. Um, so how we do this in MATLAB, there is for defining these kind of relations of one variable into another, the method is basically to tell the computer that it is a function of x. So basically this is a defining way, and then we can write m uh, into x plus c. So what basically happens is, now if I plot between y and x, suppose let me give you an example. So let me try plotting y and x, and we have to basically define before what is m and what is c, right? So let's try m as 2 and c as 1. And if we want to basically plot this equation, we have to give uh, give this plot function, and uh, give it the value of x and value of y. So maybe I want to what do I want to do? Maybe I want to uh, plot a range between suppose suppose 0 say 5, that we want a line, right, of x, and we can have the y as y, because y is the value defined. And let's do that. So I hope things will work in this sense. Yeah. Yeah, should work. So let's try this first, just to check out if our formulas are correct. Run. No, they are not. So what have I done? Hmm. Okay. So what was happening was the function for this is fplot. Just a sec. The figure has come, but on the other screen. Uh, Hold on. Okay. The strange thing is here line is not visible on this screen, and if I change it on the screen, it is visible. Why is that? Uh, what is happening? Okay, let's try it again. I think some issue with the screen orientation or something is there. Uh, how is it visible on the other screen? Strange. Okay, let me try again. Uh, okay. ऐसे तो ऐसा नहीं होना चाहिए, but still let me try doing something. Yeah. So here it is. Hmm. So basically by using fplot, I don't know why it is showing different in different screens, but anyways, using fplot, we can basically plot any equation that we define and turn it into this way. So why this we are seeing here is uh, our Gaussian function or the normal distribution function, we can basically plot in terms of equations and see how comparatively they are. So let's do that. Let's first make the Gaussian. So let's define our Gaussian function as G1 as Gaussian 1 for C, right? Or GC. Let's do that. And it will be at the rate x, right? In terms of x. And mm, so it will have CA1 as the first variable into exponential of minus x minus CB1. That was the equation, right? Let me check. 8 minute. That was the equation. Yeah, x minus BC1 by C1 the whole square, right? So by C1, so CC1 and close that whole square with the caret sign and close. Sorry, that's it. This is for GC1. GC. You can do the same thing for the other two. So let this be GP and let this be. Oh, time is also up. Okay, hold on. 5 minutes. GU uh, and this will be again uh, P P and P. This will be U A1. This will be UB1 and this will be UC1. Right now. If just we want to see how the plots will look, let's plot these uh, from the x values of कितना से कितने तक vary कर रहा है, our values are varying from, hold on, let's check it out. Our x values are varying from 18 to 45. So 15 to 45, let's plot that. So 15 to 45 and plot GC. And also now we can actually plot all these together by putting something called a hold function. So hold is on. Putting a hold at on, basically we can plot multiple values or multiple plots in a same figure. So if we want to compare those, that will be a good exercise. So let's try this. What basically we have done is we are trying to plot in the range of 15 to 45, and we are doing it in a single window. So what we obtain is something like these. So different probabilities and different distributions can be seen. And where is the third one? Third one is very small, I think. What we can actually try to see here is where others are. So cohesion curve is this one, right? And phi values are this, so probability of doing that. And we have a very high distribution, very flattened distribution of U, unit weight. And if we want to see where it will be, unit weights B1 is 0.27 because its mean was so low. In terms of that, it will be uh, quite uh, quite low. Actually, what we have done is we have basically plotted only two because the third one is not in this range. It is just a flat curve. What we may have to do is we have to increase the range. So let's put it from 0 to 45. Let's try that. Yeah, because unlike what we thought, uh, and this point of u is variation is towards the lower side, right? And c and phi basically towards the higher side of these values. So the x value doesn't matter. The whole thing that matters is what kind of probability distribution is there. So that's what we are looking at right now. We are looking at relative probability distributions of all distributed in the same figure. So that's why it's a bit distorted. But yeah, what we can do now, or we cannot if time is not there, is basically we can find the forces. So in terms of forces, how we do that? If we want to basically do C plus sigma tan phi, so it will be simply uh, like force of resistance. If Fr is the force of resistance, it will be Gc plus uh, sigma. So we have to calculate sigma as well. So sigma we can calculate by maybe taking unit weight into the component of there. So what we'll be doing is let's not do that today. Let's take it tomorrow or day after tomorrow for the lab class and do the probability calculation there. And if time permits, we'll start the finite element modeling. So what exercise what we are doing is right now is just for seeing if the probability distribution function can be done in MATLAB and how it basically explains us what happened in the limit equilibrium method part. Okay, so we'll stop here. I understand it's a bit slow because so many processes are there, but yes, that's what the beauty of the uh, better computational methods are, that we have already seen the limit equilibrium method, right? So that's so much quicker than this and does the same work essentially. But yes, we also need to understand how these are working. So let us finish that in the next lab class on Thursday, and we'll be also starting finite element method, how it works and all on that time. Okay, what time we'll be meeting on lab class, I will be telling you tomorrow. So let's close it for now. I hope if any questions are there, please you are free to ask. Otherwise, Jayantu sir is waiting for most of you. Thank you so much, all of you, for coming. Uh, if any issues are there, any questions are there, any things are there that you want to discuss, please feel free. Uh, I am. You are all welcome for that. And what we are doing forward after this will be very important part of computer applications. So be ready. Uh, Finite element modeling is a bit tricky, but very useful. Some very nice calculations and concepts will be cleared in that. But the usefulness of that method is when you realize by our examples, it will be like what can not be done by this method, something like those lines. So uh, we'll be starting that on Thursday. So let's meet then. Okay. Thank you very much. Thank you all of you, and stay safe, stay healthy, take care of your relatives, take care of yourselves. Uh, Goodbye.